So thank you very much for coming to my talk. I'm really pleased to be speaking here again at Troopers. The last time I was here was in 2018, I think, when I was talking about an entirely different topic, which was all to do with high-tag 2 cryptography. But today I'm going to be talking about BPF, and specifically about detecting and blocking actions using it. So for those who don't know me, this is my obligatory Who Am I slide. The most important bits are towards the bottom, where you see I worked for sysinternals, where I ported sysmon from Windows to Linux using eBPF to replace the Windows driver. That is open source, which is quite a new thing for sysinternals. And so if you want to contribute to that, please do, because they could do some help, because I very swiftly moved on to Isovalent after releasing that tool, where I work as a software engineer. What I'm going to talk about today, I'm going to try and make you realize that logging is exciting and something that we should care about, and something that I think we could be doing entirely differently. I'll then talk a bit about what BPF is, because I'm aware that not everyone has seen my previous talks or knows about BPF. I'll then talk about an open source tool that we've made, and we're actively developing, that will help us do that, where you can access the power of BPF purely through YAML without having to do any coding. I'll talk about what it provides. I'll give some examples and hopefully some demonstrations, assuming it works, and I'll talk about where we're going to go. So logging. Logging is exciting because, we're on the defense track, and defense is all about seeing what's going on and then doing something about it. But the problem with most logging systems is they don't really want you to look inside the box. Even with open source solutions like K-Audit, which is part of the kernel, which is obviously has the user space component audit D, you're pretty limited as to what you can do. Like, you can configure it, you can choose of the options of what it lets you log, which bits you actually want to log, but it doesn't really let you change much about it. And as much as everyone will say, well, it's open source, you could change the code yourself, you could, but you could destroy your kernel in the process, and how do you know that your change is making a lot of sense? But away from the open source solutions, if you're looking at EDRs, then they really don't want you to look inside the box. They give you an amount of configuration to choose what you want to log from what they tell you about, and that's all you can pretty much do. And so my argument is, if we have a room full of people, so we have maybe 200 of you here who know all about exploitation and attack methods, I don't think we could decide what the next technique is going to be in exploitation. The technique that comes out next week or next year that no one's ever heard of or thought about before. And if we don't know and couldn't say what that new technique is going to be, then I think we'd have to say that the people who provide our logging systems also don't know what that would be. And if they don't know what it is, then how do we know that their systems will detect it? I mean, what are we going to do? Wait for an update while there's some new technique being used around the systems? So my argument, and the argument that I want to get across today, is don't buy a logging system, don't install a logging system, but build your own logging system. Like, if change is the only constant, not the rate of change, but change itself is the only constant, and everything is changing every day, then why are we using logging systems that aren't changing? Or you can only change within a small amount of parameters. You should be able to change your logging system every time something new happens, which could be kind of daily. Now, if you have seen me talk before over the last few years, you'll be like, you're still talking about BPF. And I am still talking about BPF, which is because it's a really exciting topic. But if you didn't see the talk, I'll give a quick summary. You can find it at this tiny URL if you want to see the talk I gave at 44Con last year. OWASP Southwest also published it. B-Sides Athens published it this year as a talk, as a prelim talk to their conference. But you can find it at that tiny URL. But in summary, BPF is powerful. You mostly have to do it yourself. And it's really, really difficult. The vast majority of my talk last year was all the problems of using BPF. So in terms of being powerful, you can hook pretty much anywhere in the kernel. So pretty much any kernel function call, network op, syscall, tracepoint, you name it. And when you hook, you can run your own code, which you've written in C, usually. There are Rust compilers for BPF now, and you can also write it in inline BPF assembler if you wish. But you can write code that runs in the kernel in a safe fashion. So you shouldn't be able to crash the kernel regardless of what your code is written to do. That's the sell, because if you could crash the kernel, then you're no different to running a kernel module. One of the benefits of BPF over kernel modules is that you have to compile your kernel module against your version of the kernel, or you have to acquire a kernel module specifically for the version of kernel that you're running. With BPF, you can write code that is largely portable. We have code that will run on a variety of different kernels from, say, 4.19 through to the modern 6 branch, unchanged. We can ship that as a binary, as an ELF binary, and load it into kernels. So BPF is far more portable, which is another brilliant thing about it. And your code can access the task struct. It can pull information about the current running process. It can pull information from other places. It can store it in data structures that are shared with other BPF programs, shared with itself, shared with user space. There's a ring buffer where you can send data to user space. So it's an ideal place to observe everything that is happening in your system. But it's basically an API. It's a programming language. You have to build it yourself. And so the vast majority of BPF programs are written in a fashion where you either get something off the shelf that does a thing, and Sysmon would be in that sort of category, so Proc1 for Linux would be in that category. It's using BPF, it's using the power of BPF, but it's not really doing, not really giving you the configuration to go beyond what it can do. If you want that power, you pretty much have to write it yourself, which is kind of difficult, to be perfectly honest. The main thing is, so the ecosystem is very complicated to understand, or it's different to understand, in terms of how you go about writing your programs and how your programs are laid out. But you can get over that. The real problem is the verifier. So when you load a BPF program into the kernel, it goes through a verifier, which basically does some static analysis on your program to make sure that it exits within 1 million instructions, regardless of the path it takes, that it doesn't dereference null pointers, it doesn't access memory it shouldn't access, and it only uses helper functions that you're allowed to use. So to be clear about accessing kernel functions, you can't call any kernel functions natively. You can only call BPF helper functions that you're given. And different program types for different places where you might attach them will have different helpers available. So one in the network op stack might be able to access the internals of a packet, whereas one that connects to a random kernel function might not be able to access the internals of a packet quite so easily. So my argument is, instead, why don't we just build a really generic tool that has all the power of BPF, but all of the configuration that will let you do almost anything you can do with BPF with the tool, but built in such a way that you don't have to do any programming. And that is Tetragon. So this is open source. You can find it at GitHub, Cilium/Tetragon. You basically configure it with YAML. And I've got a 14-year-old son who can write YAML, mainly because Minecraft is configured with YAML. So if he can manage it, I'm sure everyone in this room could probably manage that. And that will tell Tetragon where to hook the kernel, what kernel functions or network ops or syscalls or tracepoints or whatever to attach programs to, what you want to observe at that point, and what you want to do about it when you observe something. So the code's hidden. You don't need to program, but if you want to, please do. It's open source. We love a PR. There'll still be issues and bugs to be fixed, and there's a lot of functionality we could all add. One of the cool things about it is it knows about data types. So within the kernel, there's a number of different structs that are important. not just like character buffers and strings, but also things like file descriptors, sockets, SKBs, which is a socket buffer for a single datagram, and various other ones. And so when it accesses those, it knows how to handle the data. And when we send data to user space, it knows how to print it out. It knows how to convert it into JSON. It knows how to present it to you in a fashion that makes sense. So if, for example, you had where you hooked had a pointer to a particular data type, in other logging systems, you often just get the pointer, which is completely pointless. Whereas for Tetragon, you're going to get the actual details of what that thing is pointing to. Oh, and it can hook things on return. If you were hooking a read function, like reading file, reading memory, reading off a socket, obviously the buffer on the entry point to that is pretty pointless because it's going to be empty, or hopefully empty. It's the buffer on the return that matters. So we can grab buffers on return, we can grab return values. As well as looking at the arguments to the function that you've decided to hook, it can also look at other state. So the process ID, the UIDs that it's running under, the binary that it's running, all the way through to the container-based stuff, namespace, capabilities, etc. And make decisions based on that. So you can, let's say here, you can follow file descriptors and track sockets. There's a number of things we can do, which I'll come and talk about those in a bit, because that make more sense. But basically, you decide what you're interested in and what you want to report, and it will do it for you. And then it will do that by hooking into, standard mechanisms like gRPC. And we can also trigger thinks canaries. So if you know canary tokens or thinks canaries, then they're a brilliant way of alerting you to something that's really important. So normally with your logging system, often you log everything, but some things are really likely to be malicious activity, and you want to know about them immediately. Well, an easy win there is to make that trigger a canary. And then that will, send you an email, send you a text message, like send something into your Slack, or whatever. So if you haven't seen like canary tokens or thinks canaries, then I urge you to have a look. They're really great. You can litter your system with them, and if an attacker stumbles across one, you get to hear about it straight away. And as I said, it's really easy to configure. You tell it where you want to hook, what the arguments are, what you care about in those arguments, and then what you want to do with it. So you might use it to replace your logging system, as I suggest. But we can also do other things. We can also build an EDR. We can block functions from running based on the arguments to them. We can kill processes directly from the kernel before the function's completed. So with a lot of logins, a lot of systems that, or EDRs or other BPF-based logging systems, they do the killing from user space. So whatever it is you've detected, that still gets to carry out. That could be like killing your system, overwriting files, exfilling data, whatever. And then they kill the process when they alert user space. Well, we tend to kill things directly from the kernel. We block the functionality from occurring, and then we kill that process dead. If you're sure that that's malicious, obviously. If you use strace is following syscalls, you could build a better strace. Why limit yourself to syscalls when you can look at individual kernel functions? Why print out all the data of all the syscalls when you only care about a few? There are various ways in which you can make a better strace. And I'll put here debug kernel bugs because we have quite a number of kernel hackers working at iSurveillance, and while they're debugging the kernel, they're now using Tetragon as their means of seeing what's going on in order to understand the bugs. So in the past, you might have used printk to print stuff out from the kernel. You might attach to a VM with GDB in order to debug the kernel using an online debugger. But actually, it's so much easier just to tell Tetragon, these are the functions I care about, show me what's going on at these points when you get hit. So we're finding use cases for it beyond what we thought we might find. So what do you get? Out of the box, you get process management, because you want to know every process that starts and every process that exits. It's really important. But we also cache all that information. So everything we know about the process, we stick into a little database in the kernel. And every other process, or every other message that we generate, we can look up the process and then just annotate it with all that information. So to save you having to join stuff up in your seam or your logs afterwards, every message will have the full history of what that process is. And, you know, as I say here, it includes things like pods and namespaces. It's container aware. If you're using a K-audit-based solution, the guy from Elastic yesterday was talking about Audit Beat, which is a K-audit-based solution. It's not container aware, and it's never going to be container aware if you follow the discussion on the kernel mailing list. So you might get the process ID in terms of the bare metal host, but what you care about is the process ID within the container, because that's your view of the world. So you know, if you're using K-audit and you're in a Kubernetes world, then I suggest you're probably losing and you probably want something better. To give you an idea of what events look like, it's all JSON. It kind of is pretty straightforward. Down this side we have the process, you know, what's being run, what arguments, etc., along with an ID, which you can then track through your seam, so you can match it up with other things if you wanted to quite easily as a straightforward key. Over here, continuing on, you've got the parent, which means you can build trees in your seam. So if you know, from any process, you can track back to exactly where that came from, which is kind of handy. Obviously, timestamps, etc. The exit event looks very similar, except, of course, it's also got an exit code, and it's called process exit rather than process execution. The other things you get are, you know, support, documentation, examples, Slack, us. You know, we've got full-time developers working on this. It's in active development. If you have ideas or you want things fixed, then, you know, we're available via GitHub or Slack. And we're intending to build out from this into sort of community where we can all share detections. If you look at the Sysmon on Windows community, there are a number of repositories of detections, which the community adds to, and we feel like that's a brilliant move, and we're going to encourage that as best we can. So we will start that ball rolling, we will write as much as we can, but obviously, eventually, if all things align, then we'll have repositories that anyone can add to, which will be really nice. I need to talk about hooks and where you find them, because everyone always asks that question, and there's no good place in the talk to put it. So how do you find where you want to hook the kernel? Well, we use this, which is the Elixir, so elixir.bootlin.com. It's a great website. It has the source for all the vanilla kernels going all the way back. You can search through it. It's hyperlinked. So if you find a struct, you can click on it. It'll take you to where the struct's defined. If there's a function, you can click on it. It'll show you everywhere that function is used, etc. It's a really cool way of navigating sources. And then when you find something, you can look at the different versions and see how that file has changed or that function has changed over time. What you might sort of typically do is start with syscalls. So I imagine everyone knows, but you know, when your user space process wants to access some kind of resource, whether it's disk, network, etc., it asks the kernel for access to those things, and that's done through syscalls. So everything that your user space process does that's important is typically through some kind of syscall or has been involved in some kind of syscall at some point. So within the Elixir, you might search for sys underscore and then the syscall name, or do sys and then the syscall name, and typically you'll find the entry point for that syscall. From there, you can then follow through the functions that get called from within there and find the place where you want to hook. You might not want to hook a syscall itself, because the buffers that are provided to that syscall are user space buffers. They're not owned by the kernel, they could get changed. Whereas you'll find in the syscall or do syscall function, at some point, if you follow the execution path, the kernel will copy that memory into kernel memory before it acts upon it. And that's the point where you want to hook, is just after that copy, because then you know you're dealing with the buffer that the kernel is acting upon. So you're reporting exactly the right thing. Otherwise, you might fall foul of phantom attacks, as talked about at DEF CON 29, where the user space program changed the buffer between the logging program seeing it and the kernel actually acting upon it. So you log that you're looking at /temp/foobar, but by the time the kernel gets to copy it, it says /etc/password, which is obviously bad for logging systems. And it was quite amusing to see the other systems that fell foul to that in that talk. It's a brilliant talk. I definitely recommend watching that. So I'll give some examples, and then we'll get to some demos. I won't demo all of these because some of these are largely trivial. If you wanted to monitor the clock changing, which is kind of an important thing, logging depends on a solid clock. Monitoring at time, always moving forwards, not being jumped around in time, because obviously that messes with your logs. Then you might want to monitor this syscall. And the YAML, I hope you can see, is as simple as naming the syscall that you want to hook, sysclock set time. The argument that you're interested in this case is index 0, which is which clock is being set. It doesn't know necessarily or care about the kernel time spec struct. You don't necessarily need to know what the clock's been changed to. You just need to know that someone's changing your clock, right? And which clock they're changing. You might then match on process ID. So in this case, we're saying ignore ID 0 and ID 1, even if they're containerized. So it could be ID 0 or ID 1 within containers. So if you've got privileged processes, we're going to ignore those. We only care about unprivileged processes trying to call this syscall. And that will then generate a detection. Every time that someone hits that syscall, you'll get a JSON event that comes out that says this thing happened. Other things you might want to monitor is the BPF syscall itself. What if someone is trying to unload your programs, unattach your programs? Someone's trying to mess with your maps. There's all sorts of things that people do that could be bad for a BPF-based login system. So you don't really want to log the syscall itself because it's an API. There's one syscall for all BPF functions, so you don't get quite such rich data from that. But you could hook a number of the functions that this syscall calls by following those breadcrumbs, as I said, from the Elixir. So in this case, BPF check is called when a program loads. Security perf event alloc is called during attaching to a kprobe, attaching to a kernel function. And security BPF map alloc is called during the generation or the creation of a map. So maps, for those who don't know, are basically the fundamental data structure that BPF programs rely on. So you can have maps that are arrays, maps that are hashes, maps that are ring buffers, etc. So almost every data type that BPF uses is a map of some description. So if someone's attaching new BPF programs or they're creating new maps, then you might want to know about it. And you can hook those with as trivial YAML as this. So this is specifying 3 hooks. None of these are syscalls, these are kernel functions themselves, and asking it to give us, in this case, index 1 is the BPF atta struct, or union rather. In the other case, it's like a perf event. In another case, it's a BPF map. It will understand what those data types are, and it will print out the contents of them when you get your event. So your event in JSON will be rich. We'll have that in kind of information. And this will just show you when people have messed around with BPF after you've messed around with BPF. So quickly talk about, before we get to the other demos, the detection versus alerting versus blocking versus killing. It's great to log everything, but sometimes an action is so likely to be malicious that you want to shout about it straight away. And that's where we would use, say, thinks canaries or canary tokens, as I said before. If you're absolutely certain that something is bad, you might want to block it, and you might even want to kill the process. When would you block and not kill? I mean, if it's an exploit that you think you've detected, why let it do the next thing it's trying to do? Like, why just kill it dead? Like, if your web server is trying to launch bash, maybe you want to kill it because it's already running executable code. Like, you might, rather than just stopping it from doing that execution, stop it from doing whatever else it was planning on doing, because you've lost control. But then equally, if you're building like a seccomp type system where you might want to lock down particular containers to only a certain set of syscalls, or, as you can do with Tetragon, syscalls with certain parameters, or kernel functions with certain parameters, you might want to limit the capabilities of a container for what would otherwise be legitimate actions. So you don't think these things are exploited, you don't think they're running malicious code, you just want to limit what they can actually do. Well, you might want to just block those functions and allow the program to continue. So give it back an error code that tells it that it's not allowed to do that. Like it doesn't have access, like it's not got enough privilege, or whatever. So there are times when blocking without killing can be useful. So I'll give some examples. So it's a toy example, but say someone wants to symlink, etc. password. Now, if you're hooking the syscall, which we are in this case, and I'll come to how we might do this better in a moment, then one of the parameters is the path that you're going to hook, the path you're going to symlink from, which would be like, slash etc slash password. But, what if you're already in etc? It might just be password. If wherever you are in the system, it could have directory traversal in, right? So you're doing a string match. The only thing you really want to match on is that it ends in password and a null character, because then you know you're at the end. So this is going to catch any file that ends in the word password. So it's not the greatest example of how you might want to log things trying to symlink, etc. password, but I'll come to better ways in a moment. But with just the black YAML text, we're detecting. And what we'll get is an event in user space that says, this has happened. If we add the green text, we're now alerting. And so I'll quickly, in the power of live demos, attempt to demonstrate that. Oop, jumped across too quickly. Right, so I'm doing this turned round. Let's just make sure we don't have anything laying around, and then we'll start. So we want symlink detect. I'll show you what that file looks like, although it's pretty much what we've just looked at. So it's basically the same YAML that I just had on the screen. So it's as trivial as that. But if we kick that off, that will start up Tetragon. It will load the kprobe. It's listening for events, so that's now listening. In this window, we could have a look at the output. So it's detected all the processes that are running. I'll create some space so we'll see something occurring there. And if we were then to link slash etc password to P, so apparently something happened. We now can see the exit of the LN process. But if we boot up a little bit, we can see the kprobe here. So this event is ln -s etc password to P, and that's its parent, which is bash. I don't know if you can all see, but there's the function called, which was symlink at, which was the syscall, and the argument was the etc password. So there's the detection. So we've correctly detected that that's occurred. So we'll quickly stop that, pop back to the slide. So if we're going to add this bit of green text now, do it as an alert, we should be able to quite quickly start this up. But this time I'll use the alert version of the YAML. So that will kick off. Okay, let's listen for events. We better remove our link it again. And then if we look at our output, we can see a bit more, maybe. That's the RM. Hang on. This is where your demo doesn't work, but let's hope it's... There was execution. Did it not catch it? Did something not occur? Maybe I did it too quickly. Maybe I need to kill that and start that again. Sorry about that. Interesting. This is a demo that always works, as they all do. Right, let's see if we can get that working. So we run it with, alert. And then we quickly have a look in here. So this is where we're at. And then we create the link. Go back over here. Oh, right, hang on. Yeah, what's occurred is the logs rotated. So there is our kprobe. Sorry, that's what was going on there. I needed to clear out the logs. So that is the exit. There's an exit. There's the kprobe, and it's got an action of DNS lookup. So exactly the same as before, but instead of just being a detection, now it's an alert. And if we were to go and have a quick look, in my Slack channel, I've now got an alert in here that tells me that someone's been accepted password. If I look in my email, I've got an email saying that someone's been looking at my accepted password. So you know, I could have a text message, I could have a whatever, right? So that's an alert. We want to see blocking and killing. I mean, we should probably do so very briefly. Right. So if I remove that again, kill this off. Start this up. Oh, we'll look at the slide. That's what we'll do first. Sorry about this. Totally unprofessional. So, blocking and killing. Same YAML. If we use the blue bit, instead of having the alert, which we could have as well, but we have an override. So we're going to say we'll override the function that's being called, and we're going to tell it what return value to give it instead. So it says don't let it run the function, just return the error code -1. And if we do exactly the same things, but we add the action kill on the end, then not only will we block it, but we'll also kill it. So let's have a quick look. So here we want to do block, just to see the difference. So that will spin up. And here, if I try and make my link, I should probably make some space, but if I try and make my link, it's telling me operation not permitted, as you can see there, and there's no such file P, because it got blocked. If we do the same thing, but this time we kill, then wait for that to start. Where are we at time-wise? Right. So we create that link again. This time we get killed. So the process was killed dead. So there's the difference between blocking and killing. But which is a kind of choice. Okay, so I talked about file issues. There are issues with matching on file paths, strings of file paths, right? Because, as I say, it could be directory traversal, then it might not be absolute paths, it might be related to a current working directory or a directory file descriptor or whatever. So, you know, not all files paths are the same, as you can probably guess. Different ways of opening files, making matching on the string of the file path really difficult. Instead, you could use this really simple representation of what's going on inside the kernel. When you open a file or create a file, it gives you back a file descriptor. And if you do any programming, you'll know about file descriptors. That's how you tell the kernel about your file in any other syscall that you use, like if you want to write to it, close it, etc. Well, in the world of the kernel, we have the task struct. So the process, every process has a task struct, and from BPF we can see into that task struct. The task struct has a point to struct files, which has a point to struct FTT, which is a file descriptor table, which has a pointer to an array of file descriptors, and every one of those file descriptors points to a struct file, which includes struct path within the file, and that points to a dentry, which is a directory entry, and that directory entry has a name, and that would be password, which also has a pointer to an inode, which is all about who owns the password file, what mode it has, what flags, etc. You know, when it was opened last, all that sort of stuff, and also as a pointer to its parent dentry, and its parent dentry in this case would also have a name, and that name would be etc. And that would have a link to its parent dentry, and that would have a name which would be slash. And it would have a link to its parent dentry, which would also be itself, or null, depending on implementation. But so you know you're at the top of the tree. And now what you've got is a file path within your mount. So also the struct file with its struct path also has a link to the VFS mount struct, which tells you about the mount point that you're within. And that has a pointer to a dentry, which is where you're mounted on the parent file system. So when you've exhausted your path name, and you've got your path name relative to your mount point, you can then go and find where your mount point is mounted, and then you can follow that up the tree to its root, concatenate them together, and now you've got a full file path. Of course, unless that's on a mount, in which case, you have to iterate. And bear in mind, you can have 2048 directories in a file path on Linux, because there's a hard limit of 4,096 characters. So if you had 2,048 directories of each one of a single character, then clearly you can have 2,048 of those will make 4,096 characters with the slashes. This can be quite a process, and in BPF we don't like loops. We don't like looping things because we have a limit on complexity. So this is a difficult thing to do. But we can do cool things with it. Didn't flick on? There we go. So we can follow file descriptors. So when a syscall or other function makes a file descriptor, built into Tetragon is a way of mapping that to the file and the actual file path. Like, it resolves all of that for you and then stores that in memory. And so if that, while that file descriptor is alive, we know which file that's pointing at. And then we can do a string match on that. And we're doing a string match on the actual path, not the path that the user provided. So it doesn't have any directory traversal. It's not relative. It's a full path. And all we need to do is hook this fd install process, kernel function, which is not a syscall, it's just a function, but it's one that gets called by everything that creates file descriptors. So open, openat, create, etc., all end up calling fd install. And that takes a file descriptor and a pointer to a file. And all we do is store that mapping. If we use the action follow fd, we'll store that mapping in a hash in the kernel. And then everywhere else that you care about that, you can refer to that file descriptor argument as if it's a textual representation of that file path. We also would hook, sysclose and unfollow the file descriptor. So if the file descriptor gets closed, we take it out of our database to keep things neat and tidy, as you would probably imagine. So if we wanted to block writing to etc. password, we can do that by hooking syswrite, the syscall that writes to files, and that takes a file descriptor, but now we can treat the file descriptor as if it's a character buffer. And we can match, so index 0 is our file descriptor. In our match, we can match index 0 on a full text match. That could be a postfix, prefix, etc., right? So now you've got proper file matching, and then you can decide to do something with it. So in this case, we're going to block the write, and then we're going to kill it. I could demonstrate that, but I'm sure you all gather exactly how that's going to look. We're going to try and write to etc. password, and the process is going to get killed, and the write is not going to go ahead. So in the interest of time, I'll leave that demo as read, but it is here, I do have it. I want to talk instead about sockets and why sockets are difficult to track. Here's, network ops are things that we care about, obviously in a detection system or a login system. The main problem with sockets, though, is that they're asynchronous. So in the world of most syscalls are synchronous. They happen in the context of the process at the time that the process asks for it. So if you want to write to a file, the kernel will, you call the syscall, it will switch to the kernel will write to the file or not, while it's holding on to the context of that process. So we know which process is trying to write to the file. We can pull its PID from its task struct. We can report that. With network operations, it's you send, say you're setting up a TCP connection. You call connect. It sends out the SYN, and then time passes while we wait for that SYN ACK to arrive. And the kernel gets on with something else, and it switches out. And when that SYN ACK arrives, the kernel's busy doing something else in the context of a different process. But it knows about the socket, so then it can send the ACK, and that's then established. Equally, if you're listening on our socket, and in comes a SYN, and the kernel replies with a SYN ACK, and it establishes that listening socket, it's busy in the context of another process, so it doesn't really know. We can't tell if we hook those functions which process has done those actions. So what we do instead is we track them in the same kind of way that we track or we follow file descriptors. Every socket almost every socket, is created by the skalloc function. If you read the kernel sources, it says every socket is created by the skalloc, but later on you realize that this TCP create openrec child, really handily named function, also creates socket. It copies sockets. And there may be a couple of other places, but mostly, if you track when sockets are created, we can map the socket to the process that created them, because the socket creation is synchronous. And then have a little database of socket to processes. And it's kind of as simple as a bit of YAML that hooks skalloc, and then skalloc returns a struct sock, which is a pointer, which is a pointer to the socket in the kernel memory, which is unique to that socket and will be the same for the life of the socket. It's like it's been allocated in the kernel. And we can use that and track that memory address by taking the return argument, saying it's the type sock, and saying track it. And on free, sk3, we'll release it for keeping things tidy. And then we can build things like, we can track TCP connects, which we can, because we know, Tetragon knows about sock arguments or struct socks, it can match on IP addresses. It can match on ports, it can match on family, etc. You want to track every time a process starts to listen, you can hook the listen K-probe, and it will tell you every time a socket goes into listening mode. When a socket's accepted, you can hook TCP set state. So TCP set state happens when a TCP connection changes state from one to another. So from listening to established, or from listening to closed, or whatever. So we can track that, and we can monitor the transition from SYN received to value 1, which is established. So when you go from a SYN packet being received to the established state, that's a socket moving into accept from listen. So when it sees the sock argument, for example, it will look up in the database, find the process that sock is related to, and it will overwrite the process ID internally, and then that will end up in your event. So your event will have the right process attached to it. And equally, when it's doing the, we follow this TCP create openrec child, is the actual listening socket being created, being copied from, or the accept socket being created from the listening socket, we can track again, and we can also track that one. So we can basically track TCP connections pretty well and start to build out and monitor all the sort of things that you might want to monitor if you're building IDS, firewall, etc. But linking your IDS and firewall to containers, to processes, to specific actions, which is something that is more powerful and more interesting than the point solutions that we normally see. What about UDP? Well, obviously UDP is difficult because it's individual datagrams. You can establish a UDP socket, and then you can send datagrams to any UDP endpoint from that socket, which is kind of interesting. So you can't really just track the socket, because you could use one socket and talk to many endpoints. So you need to track the individual datagrams. And if you track every datagram and report every datagram, that's a vast volume, and that's going to overrun your ring buffer that's getting your data back. It's going to fill your logs up. So what you might want to do is just report every datagram that's unique within a certain window. And that will give you essentially the equivalent of UDP connections being established. It's exactly the same way that Sysmon works on Windows and Linux when it's tracking UDP sockets. So in that case, it's every unique datagram within 30 minutes. So you start to see a connection to port 53. You report it once to a particular IP address. You report it once. You don't report the following datagrams, should there be some. So if you've got DNS tunnels, you'll see the start of the DNS tunnel being reported, not all the datagrams. But it's up to you. You can tune this by just setting the rate limit. So in this case, rate limit to 30 minutes, and you can use that rate limit on any event. Pretty much any event. it'll match the arguments, it'll build a key out of the arguments, and then every time it sees the same one, it will see whether you've seen that since the rate limit window. So you can tune down and turn down how often you see the same event over and over again, because maybe you don't want to. So where are we going? We're going to add IPv6 support. We currently, for historical reasons, only have IPv4 support in the socket tracking machinery, and that's mainly because IPv6 parsing is quite difficult. We already have that in the enterprise version of Tetragon, so the code already exists. It's just a case of porting that across and getting it into the open source. We have quite a program of developing for customers as customers need things, and then moving that into the open source and getting it open sourced so that everyone's got access to it. Same with file operations. We have vastly more interesting file operations in our enterprise version. And again, it's a case of extracting the hooks from there and extracting the machinery that we need and moving that into the open source so that people can get access to that. Beyond that, the enterprise version has like fully functioning sensors which collects vastly more information, which you can do manually through the YAML. We've kind of tied all that sort of stuff together based on customer requirements and for the customers that are using it. So there's a simpler user interface to get that sort of information, for example. But we are going to make our tracing policies and our output more user-friendly. So for all of the networking stuff, for example, instead of just seeing K probes firing against certain network operations, in the future, we might be able to rename those as connects and accepts and listens. And equally, in terms of writing the YAML, we can group this YAML together behind common naming. So we say, log me all the connects, and that will translate into the kind of YAML that I was showing just now. So things will get easier to use. But if you need or want the full configuration control, it's still available. You can still do all of that as well. So we'll move towards the user-friendly stuff, but you still have access to the full functionality. We'll build a repository of detections and the likes, and we will get to version 1 this year, where we will hit a certain level of functionality that we feel is stable, and then it will just continue to develop. So in summary, you're doing logging wrong, and you should be doing it better. And Tetragon will provide you with a way of doing it better, using the power of BPF, not by just utilizing BPF in order to collect the data, but putting the power of BPF in your hands where you don't have to write any code in order to access it. We can detect, alert, block, and kill. We know about files, network hops, data structures, etc., and we'll report all the information there. We are on a journey. We've still got a long way to go, and we know that. But we are going to get there, and I welcome you to join us on the way. And with that, any questions?
Yeah, thank you very much. Any questions?
Yeah, so if I saw your output from the tool you're running correctly, it's like you're translating the YAML and like building the BPF code or program that you're running in the kernel. So with the kernel supporting like something like AF_XDP, AF_eBPF, you have the option to hook into like more complex programs that you can say, okay, I want for a network capture program, I want to have a small eBPF tool that's doing like pre-filtering and stuff like that. Do you see at the future that it's not like Tetragon being like main focus to monitoring, but also like building small eBPF programs that you can like hook into other tools that are supporting something like AF_eBPF?
Yeah, indeed. Tetragon is kind of like a Swiss Army knife, so it's got all sort of directions that it can move in, and as we develop, then yeah, we're building more and more things you can do with it, and so you can just configure it to do the thing you want it to do. If you want to hook something and you want it to act on that, then yes, that's where we see it going. And what we need is those issues logged so that we can see where people want it to go. Oh, we need.
Hello? Yes? Yeah, okay. Okay. Thank you for your talk. It was very interesting to see your tool working online. Well, just a simple question. You are using hook technology behind the stage, if I'm correctly understood, and this hook technology can be used by other third-party technology like malware to remove your tracking system, or legitimate software like other antivirus or firewall to get access to the same stuff, but not re-notificating you right after their hook procedures because it's the last who gets the first notification in this case. So do you implement some security mechanisms to ensure that you are still notified or you are still alive in your hook management?
Yeah, so as I say, so the one, certainly within the enterprise version, we have those built-in systems based around monitoring the BPF syscall. And as I showed, we can monitor the BPF syscall and you can go beyond that. So all the capability is there. What you need are examples of how to do that. But yeah, so certainly you can do that. And actually, just to lead on from that, BPF can be used for malware. BPF has been used for rootkits and other things like that. But your only real solution is to upgrade your kernel to a non-vulnerable kernel in order to stop the malicious use of BPF. You're not going to turn BPF off. I mean, you could recompile your kernel without BPF support, but then you lose PCAP, so, and nobody really wants to lose necessarily PCAP, so, or the other functionality that your operating system is already using for BPF. So the only thing you can do is upgrade, move forwards, and accept the risk, limit the risk, monitor, detect, block the risk, etc. So, yeah.
Thank you.
Thank you.
Any more questions? Any more questions? No? Then thank you very much again.
Thank you.